Welcome to episode 11 of the Welding Codex. This is a podcast for those who want to learn more about the technical side of welding. We're going to talk philosophy of welding, welding codes, welding defects, metallurgy, and subjects that would bore the general population to tears. In this episode of the Welding Codex, welding engineers and CWIs Peter Kinney and Garry continue the conversation about AWS D1.1 structural welding code steel. This episode covers Clause 5. We've already covered a big chunk of Clause 5. This will cover a chunk of Clause 5, and then we've probably got one or two more episodes to cover the rest of Clause 5. So this one's going to cover fabrication, stress relief, heat treatment, backing, minimum fillet weld sizes, preparation of base metal, tack welds and construction aids, and a couple other random items thrown in there. Anyways, thanks for joining us. We appreciate you listening. Note, Pete and Garry bounce back and forth between code editions 2015 and 2020 during the course of this episode. So before we get started, I'm going to apologize if the podcast gets a little off track or turns into an Abbott and Costello routine. Oh, also, before we get going, time for the advertisements. Time to pay the bills. If you're on a budget and are looking for an affordable online training course for AWS Certified Weld Inspector exam, visit train-eng.com and check out the online course for Part A, General Knowledge, and we have a new one, Part B, for the hands-on inspection. If you like our podcast and you feel that this is worth something to you, throw us a buck or two. Go to texasweldingengineering.com. We have a donation page. You can make a PayPal donation, throw a couple of bucks in there, and help keep the lights on and keep this high-production podcast flowing. Also, if you like this material, check out my YouTube channel. There's all kinds of videos on there explaining all kinds of stuff in regards to welding. Just Google my name, Garry Pace, welding engineer, and welding YouTube, and there it should bring you right to the YouTube channel. Anyways, thanks for joining us. Now on to the episode. Stress relief heat treatment.
Go over it real quick. One is the temperatures are limited, and I have only done it in D1.1 for big parts that were going to get machined. I think it was on a bascule bridge, and we had, I think it was like a 8-inch thick base plate welded to like a 12-inch piece of plate, and I want to say that was like the gear was going to be 6 feet tall and get big teeth machined out of it, and it had, I don't think it was a full pen weld, but I think it was, extremely healthy partial joint. Something probably like beveled like 3 or 4 inches on either side, and they didn't want it to move while they were machining it. So after it was welded, the whole thing was stress relieved. And you're doing it more for dimensional changes, not really as much for microstructure changes. Like a lot of times in some steels, you may do it to really soften them. Here, what you're trying to do is get out and release stresses. There's a lot of, if you do it following this cookbook of what they have, you should be okay. There's a lot of steels that are not recommended for post-weld heat treat, and those are like our 514s, 517s, all of our quenched and tempered steels. There's a laundry list of materials that you don't want to post-weld heat treat because you will destroy the microstructure that gives the steel its strength. I think that's the best way to address that.
Yeah, and like I said, I've done stress relief on, pressure vessel components and materials like that. But, and most of it's just following, like Pete said, you follow the recipe here. And generally on structural components, you don't see too much stress relief. It's not like you're dealing with a 9018, high carbon steam line and some kind of ASME boiler and pressure vessel type situation or power piping or something like that. Generally, your structural steels, you're not going to go down that road. But if you do have to, they've got you some provisions here and some requirements and a recipe that you need to follow to get you where you need to go. Once again, before you dive into this, if you are a rookie and you get thrown to the wolves, just read. do some reading, take an extra hour or two, put together what you're going to do, and generally things will come out. And Pete said here, steel's not recommended for post-weld heat treat. Stress relieving of weldments of ASTM A514, 517, A109, grades HPS 100W, and ASTM A10 or 710 steels is not generally recommended. It's just telling you flat out, don't stress relieve this stuff. It's not going to come out good. You're going to soften if you stress relieve that material, you're going to change the microstructure significantly enough in that weld material that it's not going to be anything close to what the base material started out as. It's going to turn to mush or something. So it's not going to give you the mechanical properties you're looking for. So that's why they give you a red flag there and say, don't do this. Do not do this. And there's a whole preamble there telling you don't post-weld stress relieve this stuff. Just leave it alone. I think we beat that horse a couple times too many. So let's move on to backing. Steel backing shall conform to the following requirements. Fusion. Groove welds made with steel backing shall have the weld thoroughly fused to the backing. If you're going to use backing, you got to weld to it. You can't have it unfused. Full length backing. Anything else in here, Pete, that you think we need to cover with backing?
No, I mean the reason that AWS has a whole lot of information here on backing is it's generally either you use backing or you back gouge, or unless you qualify an open root. So that's the reason why there's a lot of information here on it. There's a lot of joint designs that have the backing in here. They have some, or they used to actually, I think, have some backing thicknesses that were minimums, but I believe that's been taken out. And that was basically so you didn't blow through your backing low. So don't use like an 1/8 inch thick backing when you're sitting there sub-arcing at 500 amps because you'll blow right through. So you need to prevent melt through. And this basically it's like it's a weld quality kind of issue. Cyclically loaded, things change once things go from static to cyclic, and sometimes you may have to remove your backing as opposed to leaving it in place. That's because on both sides of the root of where you tie into your backing, you have a perfect notch that's formed there. And that's why on cyclically loaded structures you may have to remove it. And that's subject to what that should be on the drawings as specified by the engineer or in the specifications associated with the project.
Right, and it gives you a couple of examples there, some wording on do this, don't do that you can read through and figure out on backing welds. 510 welding and cutting equipment. This is an interesting one. It's just a short one, but all welding and thermal cutting equipment shall be so designed and manufactured and shall be in such condition as to enable designated personnel to follow procedures and attain the results described elsewhere in the code. So to me, this one is telling whoever's manufacturing it, you got to have equipment that works. You got to have grown-up equipment. You can't just have old cobbled together welding equipment that how do you know this is 110 amps? Well, it's on that notch right over there. We know. If you're going to swim in this pool, you got to play like grown-ups. And that's what this is telling you. If I come into a shop and I'm doing the CWI or third-party inspection or the owner's engineer or whatever capacity, and I go in there and the cutting and welding equipment looks like something that you bought at a used bake sale. I didn't even say garage sale. I said bake sale. You bought it at the bake sale. Yeah, I'm probably going to throw up a red flag and be like, no, you need to rectify this situation. Your welders can't follow the WPSs. There's no, amperage, voltage, wire feed speed, none of that. How do I know that they're welding to my WPSs? So, thoughts, Pete?
Correct. No, I think that's generally it. I mean, it's kind of a very simplistic catch-all kind of statement. There is a lot of ambiguity to it and a lot of gray area. I know a lot of places do. They have a little notch or a little mark or whatnot to say, hey, that's 110 amps. and that's where we use for our, let's say, 1/8 rod or something like that. But we know it's that way because here we use this meter over here to check it. Well, okay, hey, we've had a thought process and we've worked through it, but it's basically saying keep your equipment in good working order.
Yeah, you're doing code-related work. Follow the rules. Welding environment. You want to go on with maximum wind velocity, Pete?
Yeah, 5 miles an hour. How fast is 5 miles an hour? That has came up, unfortunately, more times than I care to think about it. And basically, if your smoke isn't coming straight up, pretty much, you need to look at doing something. It's been a problem where just not mainly whenever you're welding in the field and you don't want to erect any kind of walls or because of either time or you don't have a sheet of plywood or you can't build some kind of little hooch or welding shelter. That's where that comes into, and the argument has been on, well, how fast is 5 miles an hour? It's been dealt with many ways, but you just build something that you can keep the wind off of your consumable so you don't blow your shielding gas away. All of those processes listed basically use gas. They don't use a flux. So that's or the flux core is in combination with gas. So
one of the common for flux core arc welding gas, it'd be like a trade name would be dual shield or something like that.
Correct.
Where you're using gas you're using a gas with the flux core filler material. When I worked in Iowa, this little hydraulic cylinder place that no longer exists, and it wasn't little, but we'd have problems with the gas metal arc welding in the spring of every year when they'd open up it started getting hot and humid in Iowa. So they'd open up the doors at the end of the building and it'd create this wind tunnel. Well, for the machining and everything else in there, it didn't matter. But for the gas metal arc welding and what little TIG welding we did, man, it would blow that shielding gas away and we'd have all kinds of porosity issues for about 3 weeks before we finally got things, rearranged and shielded and doors closed or, rectified the situation. And this is meant for, a lot of this is meant for if you're going to be welding in the middle of western North Dakota, up in the Bakken oil fields or whatever, there's a lot of wind out there. You're probably not going to be using gas metal arc or TIG out in the middle of that stuff. Stick is probably a better option, as is just straight up self-shielded flux core arc welding. So,
correct.
Minimum ambient temperatures. Welding shall not be done when the ambient temperature is lower than 0 degrees F, minus 20 C. That's generally a pretty good idea. When surfaces are wet or exposed to rain, snow, or high wind velocities, or when welding personnel are exposed to inclement conditions. Means when the weather's really cruddy, you got to build something. You got to build a hooch. You got to build some kind of makeshift building structure to keep the water off, or at least get your temperature that you're welding up above 0 degrees Fahrenheit.
Correct. I mean, so not only is it, we don't want to be making welds while it's raining. It's not only just for a better weld quality, but it's also if you put people in inclement conditions, it's also harder for them to do quality work. So I would say that this is generally a twofold statement. One is quality of weld. The other one is being able to help put the welder set them up for or her for success. That's the so I think there's two parts to that one.
Like Pete was saying, yeah, it's you're trying to set your people up for success. You don't want them out there knee deep in mud trying to weld, or the frozen tundra of western North Dakota. I'm a Montana guy. I grew up there, so I always got to kind of get in a shot on eastern Montana and western North Dakota, how windy it is. So But it's the truth. Not that Western Montana is some kind of tropical environment, but any of that tier of northern states, North Dakota, Montana, Minnesota, or Canada, these are going to come into play. You're probably not going to have to worry about 0 degrees F in the southeast states or Texas or situations like that geographically.
No, but I mean, I grew up in South Texas, and I definitely know about having to weld on shrimp boats and stuff in very wet environments and wind along the coast. So none of those were fun.
No, no, and it's a different. You got a different situation there, which is covered in wet or exposed to rain or high wind velocity. So you can get two or three of those
All in
clicked
one.
off right there. So
That's right.
definitely there's a lot of, you might not be dealing with the frozen cold, but there's the wet and the wind velocities that you've got to deal with. Conformance with design 512, size and lengths of welds shall be no less than those specified by design requirements, and the detailed drawings. Location of welds shall not be changed without the approval of the engineer. It's telling you you can't make this up and change things without the engineer signing off. So you got to follow the design.
Correct. And the those tables that they mentioned do give you a little bit of leeway. You got to look at the table, read the table, and apply it.
Minimum fillet weld sizes is 513. Um, the minimum fillet weld size, except for fillet welds used to reinforce groove welds, shall be as shown in Table 5.7. The minimum fillet weld size shall apply in all cases unless the design drawings specify welds of a larger size. Make sure that you put in the minimum fillet weld size.
Correct. Now, this is one that should also be looked at from the reverse. So the code talks about a minimum fillet weld size, but you should also be wary of maximum fillet weld sizes, especially if you have things that move or something that gets put into an area and all of a sudden the fillet weld is too big for the part to now go in because of clearance issues, and also just cost over welding and possible distortion as well. So the code has a minimum, but as a good fabricator, we should also probably look at having a good maximum size as well.
514, preparation of base metal. Now, this is where you can get into all kinds of trouble. To me, this is just common sense. I don't even know how to start, but
Well,
obviously they've put in, a whole section here because obviously somebody out there in the universe wasn't cleaning things or preparing the base metal. So I'll just dive in and
this one has a point of contention, and I know some folks have really picked on D1.1 for one of these, but you're right. The first part, I mean, general, it just needs to be clean to make a weld that's the quality requirements. Uh, that's a first real general, I would think, easy to understand kind of statement. The next one is about mill-induced surface defects. A lot of materials made to ASTM A6, and there are allowances for defects. So this is talking about what. So if we have like a fin or a crayer, I mean, don't put the weld on base metals that have a problem. That's pretty easy to understand. I mean, what do you think, Gary? There's nothing? Is there anything complex about that one?
no, this comes down to, educating your welders and then you as an inspector or an engineer or whatever your role in the food chain is. You got to be able to understand that, fins, tears, cracks, slag, or other base metal defects. You got to be able to recognize these and realize, okay, we can put in a beautiful weld, but we're welding over substandard material or material that's got a defect in it. We're not accomplishing anything. You're not getting where you need to go. So you need to understand that, you shall not be placed on these surfaces. It means don't do it. If you're welding on crappy base metal, don't stop. Figure out your path forward, get a new piece of material, or see if you can repair it, what your situation is for a repair situation, what your path forward is.
Yeah, so the next one is talking about scalar rust. Okay, I'll be honest, I am a big proponent of you weld on shiny material, but that's not what the code says. So like loose scale or thick rust, it has to get removed. But when it's real thin, now this is all subjective about what is thick and what is thin, can be allowed if it's thin, and it can withstand the vigorous hand wire brushing. That's, I mean, I can see if you have I mean, the Hulk out there wire brushing is going to be a lot different than a person that's probably 100 pounds. So, like I said, that's another subjective one, but it allows it unless you're dealing with cyclical loaded structures. And then it's for your flange to webs, all the mill scale has to be gone. And like I said, I'm a big proponent of bright and shiny sets you up for success. The more stuff you weld over, the more chances you have of a problem. I mean, I know a lot of fluxes are designed to handle some stuff, but the less it has to handle, the better off you are. What do you think about that one, Gary?
Yeah, there's some situations where you might be able to get away with it and punch through it, but generally you want to have it's shiny material. You don't borrow trouble. I used to have a boss that said don't borrow trouble. And to me, if you start welding, making a habit of welding over mill scales and rusts and material like that, you're just asking for trouble. You're borrowing trouble. So you're trying to set yourself up for success, and a little bit of grinding and preparation of the weld metal goes a long ways. And that ounce of prevention is a pound of cure type of thing.
Correct. I remember when I was first starting out as a welder, and I was the youngest one there, the least experienced one. The way we addressed that was give Pete a 9-inch grinder and let him grind for a couple hours, and everything I mean, a 9-inch grinder makes a lot of things disappear real fast. Put either a big disc or put a big cup rock on it, and the weight of the grinder, and you don't have to push down very hard, will make a lot of all that disappear, bright, shiny metal, and you're right, you're not borrowing trouble. I like that, Gary.
I'm a storehouse for these useless sayings. So, okay, so 514.4, foreign materials. Okay, we talked about rust and mill scale. 514.4-1, surfaces to be welded and the surfaces adjacent to the weld shall be cleaned to remove excessive quantities of the following: water, oil, grease, other hydrocarbon-based materials. Welding on surfaces containing residual amounts of foreign materials is permitted provided the quality requirements of this code are met. So what this is telling you is we're dealing with carbon steel. We'd like you to get it as clean as possible, but you don't have to get it as clean as you would if you were welding a duplex stainless steel, a nickel alloy, or let's say a titanium type base metal where you can't have anything. There can be absolutely nothing on those base materials when you start to weld. Whereas this is saying, okay, we're welding with carbon steel. All right, we can punch through the oil or the grease or the cutting fluid. Wipe it off, get it as good as you can, but it doesn't have to be just absolutely surgical level of cleanliness. That's what that's telling us. Get it as good as you can and make a good attempt at it.
And also if you're welding and all of a sudden you start to see a bunch of porosity in your weld, as the last sentence says, you have to meet the quality requirements, you stop and you figure out what's wrong. I wish, Gary, I would have known what conversation brought this into the code. I don't know what it is to provide some history on it. But what I could easily see is if someone was working on, let's say, a sub-arc tractor and they got a can of WD-40 to squirt on a bolt, and someone cried that all of a sudden that spray drifted 5 feet and got on the weld area and you can't even see it. I don't know. I'm just making up a story of how this section got into it, of where it's quantities that you can't even really see, kind of. That's the way I look at this. If you can't really see it, it's probably clean enough. If you've done a good scrubbing on it, Now, granted, if you have all your plate in the yard, you got or in your shop, and you got an overhead crane that leaks oil on it, you need to get a degreaser to make that oil disappear. Don't just weld over it. I do not think that's what the intent of this is. To give you free reign to weld over blobs of grease or big oil stains. It's the You're right. It's not surgical clean. It's like, hey, that looks reasonably clean. I don't see a oil sheen on it. I don't see standing water. It looks dry. That's what that is for. Unfortunately, it is subjective. We're human beings, and there are probably those that take it to the extreme of either welding over a pound of grease that just dropped out of the forklift to wanting everything wiped down with 10 acetone wipes with Q-tips. So we're grown-ups. Let's figure it out.
You're going to have to use a judgment call there, and you're going to have to use your best grown-up judgment and professional judgment, and because there's a lot of different cutting processes, cutting fluids, like you say, and we're big boy world, like you say, there could be hydraulic fluid and you wiped it off. It doesn't have to be, super clean that you can do surgery on it, but you've got most of the cutting fluid wiped up, or most of the hydraulic fluid from the leaky forklift or whatever. You've got most of it wiped up. There's probably some micro level of it there, but yeah, you can weld. And with some of these processes, you're probably going to punch through it and burn it off anyways. I say that, and then somebody's going to come back on me. You said we could punch through. No, you're not going to punch through 3 inches of grease or catch something on fire. You got to use some common sense. Skill of the craft, I think, is what we used to call it at the Hanford site.
Sounds good.
Welds are permitted to be made on surfaces with surface protective coatings or anti-spatter compounds, except those that are prohibited, provided the quality requirements of this code are met. This covers anti-spatter compounds that you might use when you're gas metal arc welding or using one of those processes, so you don't want to have spatter on there.
Another big one is weld through primers. That's another one, because if a lot of times things may be pre-blasted and they put a weld through primer on there, but to prevent flash rusting, etc. My biggest thing about this is make sure you're using products that are designed for it. Don't just use like any old paint and say, oh, we can weld through it. Use products that are designed and tested for this application. They exist. They're not expensive. And if you follow directions, if you goop on a whole ton of either one of them, you're going to have problems. Just skill the craft, Gary.
And when we definition skill of the craft, that means that the craftsman should have a basic set of knowledge, is an accepted base knowledge for that craft as a welder or pipe fitter or iron worker, that, just common sense. I shouldn't have to tell you this every time that you have learned this. This is just a baseline set of knowledge. 514.5 mill-induced discontinuities.
So this we touched on this briefly earlier on these. Basically, they can exist within. There's a level. This one, it's table 7.4. I think the older version is 5.4, and they can be repaired. And if they get to a certain size, you have to report them to the engineer. One good way I've seen dealing with this was we're welding big plates together for a web for a girder, and there were issues on one end. Well, it was just flipped around and welded to the other end. The good end was welded, and the other end became the drop. All of a sudden, we didn't have to worry about repairing anything. But there's provisions for how to repair discontinuities. And that follows down in the paragraph right below the acceptance criteria, where it goes through the size of the defect, how you have to find it by, the applicable ASTM inspection standard for straight beam UT. Then there's a lot of the percentages for how the material can either be for thickness, for length, And it's basically we need to read through each one of these whenever you have a repair. And I would document what these are to make sure that you fall within the X, Y, Z dimensions for the indication for it. Then the next one, Gary, which I'm assuming the old one was 5.14.5.2, the repairs. It talks about how to go through the repair of it, joint preparation, material trimming.
Yeah, and that's what's listed here is it just gets into the, the repair. My thing, I don't know how deep you want to dive into this, but to me, the repair thing it's a documentation thing. Follow the recipe and then have a systematic way of approaching repairs. I worked in a situation where we had paperwork, and it wasn't, we didn't do structural work, we did pipe work, and we did some small pressure vessels and tanks. But what there was a well-defined repair method, and it was very methodical where you would, the welding engineer was the person responsible for calling out the repair. Okay, the NDE found a repair in this area. Okay, the welding engineer, which was me, would come up with the recipe. There'd be like a little packet generated. Okay, you're going to grind out from this point to this point. You're going to do this, 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 and this. You're going to grind it flush, whatever. But there was a very detailed repair methodology that we followed. And to me, that's probably as important as what is written down here. You just can't go at repairs in, a haphazard manner. You need to document it, that you did it right, have your documentation that once you got the repair done, that you passed NDE afterwards. It takes a little bit to get into it, but that's pretty much what I got to say on repair.
Yeah, I would say I think you have a good assessment. When I used to do work for the state of Pennsylvania, they actually came up with a like pre-approved ways of doing repairs that were common for base metals on heavy sections, and it was follow the recipe, document what it was, document what you did, document the end outcome, and that's basically what it comes out to. For that. And I think I'm not sure if we need to go much more into it, unless someone had a really good repair situation that they wanted to send in that we could kind of talk about for mill-induced discontinuities. But I think that's I don't know if we need to beat that one anymore, Gary.
No, I think we pretty much hit that one. So that gets us out of repairs.
Okay, so joint preparation. This is how are we making our bevel? And it gives a laundry list of what you can do. I mean, grind it, chip it, gnaw on it. So it walks through all that, but except for oxygen gouging. And it says you can only use that on as-rolled steels. And the reason it gives you a laundry list of what you can do, but then that one exception is because oxygen gouging is extremely hot. And that goes back to the changing of our microstructure. So that's, I think that's all we need to really say about that one, Gary. Unless you got some words of wisdom on that one.
No, I don't have much on, joint preparation. Like you say, the oxygen gouging is pretty much the one that's the red flag. But most other processes may be used, but that oxygen gouging throws up a big red flag. And if there's some other process that you want to try, you can use it, but you just got to get the engineer to sign off on it. If there's some super secret special, way that you're going to bevel your plates and it's not listed here, the engineer can sign off on it if there's something that's outside the rule book.
All right. And then the next one, which goes along with it, is material trimming. And this is really only for cyclically loaded structures. And this is where you need to cut back the material, and it gives a whole list of different ways that the material has been processed. And basically what the whole goal of this is to potentially remove micro cracks. If the material is being sheared and it's thick stuff, you could have micro cracking there. rolled edges of plates, you could have issues there. So that's why it walks through different scenarios and the amount of material you have to remove to get in quote a safe zone where there's no problems.
What do we got up next?
We got thermal cutting processes. Basically, that allows electric arc gouging, including plasma, oxy fuel cutting. Those are all allowed in here.
Yeah, so it gives you a whole slew of different options. So you're not just stuck to one way to cut it. So
Exactly. Um, and along with what you said earlier, if you got some other super secret process, it can be approved, or maybe another one that's anything that you could come up with that's not in that laundry list can be approved. Profile accuracy. That's basically making sure can you cut the profile of whatever you're trying to cut out, cut it straight, cut a shape. That's all that's done. And the reason in here for cyclically loaded structures, freehand thermal cutting isn't is only done with permission. It's more likely to produce notches with freehand cutting as to following a template or a straight edge or like a machine cutting process. It's all about the notches that can then be a stress concentrator for a fatigue crack to grow in the freehand cutting. There's been multiple incidents where that has caused issues.
once again, it gets back to what we've been preaching is as you get into cyclically and dynamically loaded structures, there's just so many things that can go wrong. Things that might not be a issue when you're welding farm equipment or, putting something together for your garage. You start having the same defect or discontinuity on something that's cyclically loaded or a dynamically loaded structure. It can be a fatigue situation that it might not be an issue now, but 7 years down the road and 120 million cars going across that thing, then you got a different issue. You got problems. You got a defect that's going to take down a bridge or a structure.
Yes, and that basically plays in roughness requirements are also the smoother, the less likely of an issue. And how we have gouge and notch limitations that all need to be met. That's why I know some fabricators to get around all of this, especially on which the next subject that we were going to go on to is reentrant quarters. They actually drill them, and that removes almost all of their issues. They're not borrowing any problems by doing that. It takes a little longer, but they use a big mag drill with a slug cutter, and life is easy. They don't have to go and measure anything because a drilled hole is magnitudes smoother than anything cut by one of these oxyacetylene or oxyfuel processes.
Well, and I think what the code too is looking at is you might have the greatest cutter, and I mean oxy-fuel man ever or person, and they might be able to do it. But if you get that apprentice or a guy that's been in it a couple of years, and you go have him make a cut, and it's not nearly as smooth. So that's why they pay so much attention to this cut surfaces and the roughness. And like Pete was saying, you go with a drilled hole or a mechanically cut out hole, you're going to have infinitely less problems, and it's going to be a lot smoother than even what the best welder can cut out by hand.
Correct.
All right. How about 516 weld access holes, beam copes, and connection material? Anything to add to that, or is this one of those ones where we're just going to say read it and run with it?
Well, a lot of what we've already discussed is basically what is covered in here. Here it has some sizes of that you have to look at following. There's some requirements, especially for galvanizing it, what you have to do there, and that's all about having the right profile. But I think we have basically covered everything. One thing just to be aware of when you're doing all this stuff in heavy sections and you do decide to go and use a flame process, you have minimum preheating requirements, and a lot of these is grind to bright metal, and you have to inspect the surface. And just so you're aware of, visual may not just be the best way to define these little indications. It's not written in the code, but going to mag particle, which is a cheap and easy way to also look for little indications that you might not see from the eye, would be a good way to deal with, especially when you're dealing with real heavy sections and you choose to flame cut as opposed to drill or machine.
Yeah, and like you say, with PT and MT, they're not super expensive, non-destructive testing methods, and they'll find a lot of surface indications that might lead to problems later on down the road. All right, 517, tack welds and construction aid welds. General requirements. Okay, here we get in with tack welds. Tack welds and construction aid welds shall be made with a qualified or pre-qualified WPS and by qualified personnel. So, your person that is doing the tack welding has to have qualifications. If you qualify them as a welder, a full-on welder, they need to have paperwork. Or if you qualified them as a tack welder and went that provision, they need to have paperwork. You can't just grab a guy off the street or one of your laborers or something and say, okay, dude, you are now the tack welder. I need you to just start tacking this mess up. You need to have paperwork on them.
Yep, that's exactly true, Gary. One of the other things that really this is where in cyclically loaded structures, there's requirements for the engineer to give guidance, because the fabricator may or may not know where some of these exclusion zones are, or tension reversals. Those really need to be on the drawing, and then that needs to be communicated also to the shop floor. One of trips that was for a mistake like this was we had some big girders that were at a field site, and I want to say they were like 12 foot tall. They were big railroad girders, and someone took angle iron and just welded it right in the middle of in the web to the ground so they wouldn't fall over. Well, the problem with that is they were made with no procedure at all, and they were just welded up, and then they basically just bent the angle backwards and forced to break it off. So we had to go and grind them smooth, perform mag particle testing to make sure that it was all good. So tacks, while it's just like, well, it's just a tack, a tack can be more than a tack, especially placed in the wrong spot.
Yeah, and you can get into situations where, depending on the material, you just tacked it, but it was a quenched and tempered material. Maybe you've introduced some kind of stress concentration into that material. You don't, as the welder or the inspector, you don't maybe have the exact information of just how critical that particular location is on that beam or that girder. Then it might be, you might have just introduced a catastrophic failure point to something. You don't know. That's why we got to try and follow the rules. Tack welds that are not incorporated in final welds and construction aid welds that are not removed shall meet the visual inspection requirements before a member is accepted. Tack welds, you can't have cracks, you can't have porosity, you can't have a bunch of defects, or your tack welds, if they're going to be incorporated into the final weld, they need to be quality. Because you have a crack in a tack weld, or you have porosity or some issue in a tack weld, you're going to chase that problem's going to go all the way through. It's just going to follow you all the way to the face of the weld. So you need to make sure that your tack welds are quality.
Correct. And there's a subset when we get into these tack welds that are incorporated in the final product, is when you deal with subarc, you get a pass on a couple items. And the reason you get the pass is subarc has the ability to penetrate very deeply, and it can consume or kind of chew up what it runs over, including tack welds. But as you said, I mean, we can't have crack tacks. That's not something. But what we can have when they're consumed by submerged arc welds is your preheat for single pass tech welds isn't really required, but they can't be really big. So you can't have them get over, it's about 3/8 of an inch, or where it changes the contour of the surface of the submerged arc weld. And this, you really only run into problems in smaller, long, let's say like a flange to a web girder, where you may have tack welds that are 1/4 of an inch in size, 3/16 in size, and then you have a fillet weld going over them that's only 1/4 of an inch. All of a sudden it's like, hey, why is like every 3 feet or 5 feet, all of a sudden there's a little ripple? We can't have that. So you would need to kind of knock them down with a grinder before going over them with a sub-arc. There's a couple other ones. I mean, there's a list of them going through there. But what I'll also say about this is, if you're in the qualification kind of area, what I have always tried to do was use the same tacking process during my qual as I want to use in production to do this. And I usually put a macro there so I can tell someone that if they ever say, hey, how do you know it's consumed? I have a little picture to show them that, hey, there was supposed to be a tack weld there and there's no difference in the weld metal. That's just, though that's associated with qualification and not fabrication, that's a little lesson learned I got there.
Oh, and another one that we kind of glossed over, but gets back to acting like a grown-up and doing this stuff correctly. Tack welds incorporated into final welds shall be made with electrodes meeting the requirements of the final welds. These welds shall be cleaned prior to incorporation. So if you're doing a weld and it's, a 90 KSI material, you can't be using 60-10 and then incorporating those tack welds into your final weld, or 70-18 or whatever the material is. It has to meet the final weld requirements, the requirements of the final weld.
Good point, Gary.
This is something you need to take into consideration before you turn your tack welders loose. You can't do even though it's going to hold it if you're going to remove it and it's not going to be incorporated, yeah, you've got a number of different options there. But if it's going to be incorporated into the final weld, you need to make sure that it meets the requirements of the final weld. How about 518 camber in built-up members?
In camber and built-up members, this is where you're building, let's say, an easy example is a plate girder is where it comes up. And you're going to have shrinkage. So what it's talking about is make sure you include that, or try to include those kind of shrinkages before you cut the material. You may need to cut it a little long or a little wider to handle that. That's the gist of that section right there.
Thanks for listening. Hope this podcast was worth listening to. We're going to have more content coming out. Also, if you want to shoot me an email, gpacex@gmail.com. Give me some ideas, or maybe there's some questions that you'd like me and Pete or me and Joel to answer in regards to welding codes, filler material, or any other material joining question that you might think we have a shot in hell of answering. Anyways, thanks for listening. Take care. Pace out.